But do the honor, please.
Right, we are at time, right? So relational AI time, exactly. Thank you, Dan. And this will be the last hour you have to suffer through with me. And after me, that'll be Mahmoud's turn. So far we have discussed two problems, or two kind of formulations. One is the worst case output size bound of a given phone conjunctive query, and the other one is an algorithm to achieve the runtime that is predicted by the bound. And now let's look at more kind of practical queries and see why the worst case optimality is simply insufficient to capture real queries. So here are some examples. Consider the problem of detecting a 4-cycle in a graph, for example. In this case, we have edge relation, and then we would like to know if there are 4 vertices, A, B, C, D, for which you can go from A to B, B to C, C to D, and back to A. Now, if we apply the worst case output size bound on the output of the query, then it's just 1, right? Because it's just whether or not the cycle exists. So just 1. If we apply it on the body of the query, which means you forget about the variables that we are projecting away, then this will be quadratic, because the number of 4 cycles is at most quadratic. You can plug in the AGM bound and you'll get E squared. But from a fantastic paper, Alon, Euster, and Zwick, who is here, we know that this query can be answered in time something like e to the 1.5. So obviously our framework so far it's on this end or this end, depending on where you apply it. But the actual answer is right in the middle. So that means that there's something missing in worst case optimality framework, right? Now, if we, from the same paper, we know that a cycle of length k can be detected in time, something like e to the 2 minus epsilon, where epsilon is a function of k. So the longer the cycle is, the smaller the epsilon will be, but it's roughly something along this line. And if we apply, matrix multiplication type of techniques, then we, depending on the density of the graph, we can get different, better exponents. But our framework doesn't really capture the matrix multiplication type of join operator just yet. So we'll focus on this type of results. So another example is, let's say you would like to count the number of k walks in a graph. So what that means is that we have k plus 1 vertices from x1 to xk plus 1. And we want to know if, how many ways is there to walk from, x1 to xk plus 1. Now, in this case, if we apply the worst case size bound to the body of the query, then we'll get something like e to the k over 2. That's a terrible bound. The longer the walk, the higher this exponent is going to be, even though the output size is only 1. Right? And we know, I'll show you later, that we can answer this query in linear time, essentially. It's just k times e. So it is in between, but it's closer to 1 than to this exponent 2. Or if we take a conjunctive query with an inequality like this, x, so this is a path of length 3, x, y, y, z, z, u. And then we require the first and the last vertices to be different. Then in this case, again, we know that we can answer in linear time, but both of the bounds are either too extreme, it's 1, or too high, it's quadratic. So we basically need 2 new ideas in the framework. We need to introduce two new ideas. So idea number 1 is that we have to introduce an abstraction to deal with aggregation queries. Because you saw an example of a counting, number of paths or something, right? In real databases, you will see min and max and summation and existential quantification and so on. And we cannot come up with a new algorithm for every new possible aggregation. So if there's an abstraction to abstract away all of those details so that we can focus on a generic class of queries, that'd be great. So that's idea. We need idea number one. And idea number two is that we need a better notion of optimality, because worst case optimality does not make the cut due to some examples earlier. And here you will see that we are kind of venturing into fine-grained complexity, parameterized complexity, and so on. And I hope that this program is going to help us, unify, or at least we learn from each other, so that we can develop together a theory along this line for these queries, for these very generic classes of queries. So idea number one is something that we learned and studied from the AI literature, especially in the 80s. And we are going to use a generic class of queries called the sum product query, and it goes like this. So the input is a collection of functions. So just like before, we have a hypergraph, and for every hyper edge, there is a function, sometimes called a factor. So you just think of this as a relation, but now a relation, for every row in the relation, there's a value. It could be a real number, it could be something. So it's just a tiny bit beyond relation, right? And then the problem, instead of existential quantification, now we have a sum. So we are marginalizing away some variables, right? So those are variables are called bound variables. And then whatever we didn't marginalize away, then those are the free variables. So this is a sum product query. Yeah? So easy examples. In the conjunctive query case, we could have, let's say, a triangle, and then you marginalize away A, B, and C. And by the way, on Thursday and Wednesday, there'll be a lot more information about, the semi-ring and the power that the semi-ring brings into the expressive power of those queries and so on. So this is one example. The Boolean semi-ring, you can express the problem of detecting a triangle this way. So the sum becomes OR, and the product becomes an AND. Right? But this is nothing but exactly a special case of this query. Or if we have, let's say, a count query where we want to count the number of paths of length 3 for which the two ends are different. In this case, we think of every edge relation as a function that maps to 0 or 1. So if the edge exists, then we map to 1. If it doesn't exist, we map to 0. And so the sum product becomes a count query. Here, I intentionally put a group by variable in front. So we are summing away. So for every A, we are counting the number of BCDs for which you can go from A 3 steps away, so that the last variable is different from A. But you can vary this, with different free variables, with different bound variables, and formulate very different problems this way. So this is the first abstraction, and this is the one that hopefully, by the time the AI portion of this workshop takes place, you'll see a lot more of this. So it's not just sum over a product, but you could have a circuit, sum over a product of a sum over a product, and so on. And that turns out to be extremely powerful in expressing inference problems in graphical models, for example. Okay, so that's idea number one. Idea number two is that we really need a better notion of optimality, because before, worst case optimality was just this, right? But now, as we have seen, the output size could be very, very small, right? And of course, we have to process the input, so there has to be something in the middle. So now our notion of worst case optimality, or new notion of optimality, will be something like input plus some parameter, some function of the query, and worst case maybe, satisfying the same thing, plus the output size. If we chose this function to be this, then we fall back to that. But in some cases, this function could be a lot more refined. It could be anywhere between 1 and and that quantity. And depending on the query, obviously this is a function of the query. So this is what we are aiming for.
So it looks like we've moved to talking about the output size of the query, but not the worst case output size. And we moved, like the D is now D and not D prime. And the D prime is now in the supremum. Like how are those the parentheses going there?
Right. So D is still our database. So the database is fixed, right? And we have the statistical profile of the database. This is also fixed. So these are just the degree constraints, for example. But now we are maximizing over all possible databases which have the same profile of a function that is a function of D prime and Q. And so this one is still the fixed database that we are. Yeah. So D plus QD is the price that we have to pay. There's no other way around it. But hopefully we can reduce this down than the red thing that we have over there. Okay. Now this is only good if it's actually accompanied by kind of an algorithm to somehow achieve this bound. And so I'm going to talk about a class of algorithms to achieve this bound. And the algorithm goes like this. So the framework goes like this. So we have a database D. We are supposed to answer this query Q, which is a sum product query. And then this is the output, right? So what we will do is we will kind of, from the database, we'll compute an intermediate representation. So that from here it's actually very easy to extract the output. So that's kind of a meta query plan. And this intermediate representation is essentially this quantity here. Like the time it takes to compute this is exactly that quantity. And hopefully this will be a lot smaller than that red quantity. Yeah.
So the last thing is what's that optimal? So is there a name for the right down or this?
I don't think there's a name. So if the query was very specific, if we knew the query to be, I don't know, for cycle or whatever, right? So then I guess you could think about some kind of fine-grained complexity or parameterized complexity, of which I'm not qualified to talk about. But it's certainly pointing that way.
What is QE?
Yeah, so I was planning to say that instead of answering this query, we break it down into two queries. We will come up with QH, we'll come up with QE. So E stands for like extraction. So you just extract the output from this intermediate representation. But I wrote down these notations a while back, and now I don't remember what the subscript H stands for. Sorry about that. But it is basically, break a query into two halves. The first half is just to achieve this, make it as small as possible, and from here you just get the answer out easily. All right, guys.
Do you want to formally put any restriction in what QE can do, or like how do we think about QE? Do we want to do something very simple, have some specific properties, or?
So for this talk and for all I know, my QE is just this one.
Okay.
It will be basically somehow from this intermediate representation, we can run a variable elimination algorithm to get the output. And the runtime of this will be linear in the input, which is this guy, plus the output. So it's basically this term plus this term, or in other words, this term plus this term. So that's what QE is. I would like to kind of simplify the query plan as much as possible so that it will follow this script. And so most of the complexity is just to come up with this window. And I'll give some examples. It probably will make more sense.
I mean, is there an argument that there is no other way to evaluate the query so that it will have a lower worst-case complexity? I mean, or is it lower worst-case complexity when you follow this particular plan of decomposition?
Yeah, so the question is, essentially, is there a way to prove lower bounds of some sort, and whether or not this generic query plan is going to achieve that lower bound? That's open. I'm not qualified to say anything about lower bounds really, but I will give some examples in which this does seem to achieve some of the lower bounds that we know for some queries.
If you
think about this plan from a practical perspective, is it sometimes possible that this intermediate representation could actually be more useful to the user than the entire huge output? And for this reason, it makes a lot of sense to try to, come up with good intermediate representations that can do that, and then try to prove like strong results on.
Yeah, definitely. Yeah, great question. So one of the very popular intermediate representation is the factorized database that we'll probably tell you more about. And from there, you can extract the answer very quickly, but you don't even have to kind of realize this answer, right? You can just compute this representation and keep it as small as possible. So definitely. But factorization is one way. You could have a circuit to compute this thing. And that's what the tensor decomposition part is. Okay, so now I will, in order to explain this kind of meta query plan, I'm going to explain this part first, the variable elimination part, because it's the easy part, where we get a runtime that is this, the cyan color plus the output size. So that's the easy part of this. So variable elimination is can easily be explained with a couple of examples, and you will kind of get it immediately. It's a generic way of doing dynamic programming, and it applies for any semi-ring. So it goes like this. So suppose that you have a count query where you want to count RAB, SBC, and TCD. So in this case, let's abbreviate or overload notation a little bit. I'm going to use RAB to denote a function, not just a relation, that indicates whether or not AB is in R. So this is kind of an indicator function. Same with S, same with T. This variable elimination algorithm was often cited to Zhang and Poole in '94, but I think it was even discovered before then. I'm not 100% sure. Probably someone from the AI literature would correct me. And it works over any semi-ring, not just the sum product, but it's easier to do this with sum product. So here, counting becomes, sum over ABCD of this product, right? Because this product is one if and only if there's a path from A to D. If, counting is the same as computing the sum product. So all we are doing is to play with the distributivity of sum over product. So we can push the sum inside. So once we push the sum inside, then here we have a relation, TCD. And if we are summing over D, then that means we are counting for every C how many Ds are adjacent to the C. So think of this as a graph. It's just counting a number of edges. It's just a degree of the vertex C, right? So that currently can be done in linear time. So once you have that, then now you have a function over, for every C, it will give the degree of the vertex C. Right? You can store this in a relation. And then we play the same game again, but this time we're pushing the summation over C inside. Right? So here now we are summing over the degree of this vertex C, and we have to check whether or not that vertex C is in the BC relation. Right? So this subquery can also be done in linear time because all we have to do is to scan over S for every BC. You do a lookup into this degree of C and just sum it over. And because we are summing over C, so this means that we do this for every B. Right? For every B, just scan over all of the C's and sum up the degrees of the C vertex. So that's linear time again. And now we have another intermediate relation, V of B. This is no longer degree. This is like for every B, how many 2-hop Ds that you can reach from B. So it has kind of a combinatorial interpretation if you want. And then, and I think this is what a human would do. If you have to actually program this, it would be exactly what a programmer would do, except that it's completely automatic. Now, in the database literature, if you read database textbook, you will hear words like aggregation push down, projection push down, predicate push down. That's exactly this. That's just this idea. Applied to different algebra, but it's exactly this idea. So that's the variable elimination algorithm. Okay, now there's one extra idea that was basically introduced by Martin Grohe and Daniel Marx in 06 in a beautiful Soda paper. And then we kind of try to generalize that to the sum product setting along with a slightly more general query class. And it goes like this. So suppose that you apply this idea on this query. And so if you were to push the summation over f inside, right? So typically what you would do is you would factor out everything that is not dependent on f, right? Because the more you don't have inside, the easier the subproblem becomes, right? So you would factor everything out. However, we can introduce the following idea. So if you look at this, there's actually a function, a factor, B, C, D, E, that actually depends on E and D, right? So it's kind of this little subproblem. If we didn't have this factor, then this subproblem will take quadratic time, because for one single f, you could have n different E's and n different D's, right? So then if you want to iterate over the answer, you will pay quadratic time for that. However, with this idea, what we can do is there are many pairs E and D that will never occur in the T table, right? So it'll be a big waste to just compute over those pairs, because they will not occur. They will be kind of killed off by the DE entry here. So what we do is we project this table back inside of this subproblem. So this projection just say that, well, this will be 1 if DE is an entry that will be relevant later on in the computation. Right? Because if we didn't do this projection, then we would have computed this blue subproblem for pairs E and D's that may be irrelevant later on. And if we are doing dynamic programming from the bottom up, right? So the main problem with bottom-up dynamic programming is overcomputing, right? And this is sort of like mimicking the top-down part of dynamic programming by doing the projection from the outside back into the subproblem.
Not understanding of the notation. T is at the same time additive 4 and additive 2.
Oh, yes. So I have to define that. So this projection onto DE of T, this is a new function. And this is defined to be 1 if there exists B and C, for which TBCDE is non-zero, and it is 0 otherwise. Yeah, so the whole point of this is that if there were entries that were 0 eventually anyways, then we shouldn't really compute over those entries, because they will be killed by the multiplication outside. Right.
So do you know which relation is more convenient for your query?
Yeah, so the question was essentially in which order of these variables should we do the elimination? I'll come to that, but it's NP-hard in general. But here, this idea is just to say that, another way to say this is basically in databases, a very important problem is subquery decorrelation. And this is exactly that. So here we have a blue subquery. And however, we have a later query in which there's a relation that's actually decorrelated with the subquery. So we just project it back into the subquery to make it smaller. And the worst case size is exactly went down, because now it's just n to the 1.5. Due to this, we kind of killed off the entries that are not relevant. Okay, so now that we have that, then we have a new factor, because we are marginalized away f. So now we have a function or a factor m1, and then we play the same game again with some projection from the outside. So we have a new factor m2. And finally, here we end up with kind of a triangle query again. And this query, we know that we can evaluate again with worst case optimal join in n to the 1.5. So you can see now how worst case optimal join actually plays a role in query evaluation with projections, right? With variables eliminated away. And this whole query now can be answered in time n to the 1.5.
These are numbers the M1, M2.
Oh, so this M1 is just the result of this.
This is a number.
It is a function, it's a relation over three variables actually. For every D and E, we have the summation over F corresponding to the D and E.
Okay, so this is a relation.
It's a relation with three columns. And yeah, so basically the width of this query is going to be 1.5. It's called the fractional hypertree. And that the same idea works for conjunct, CSPs. That came from the paper by Groen and Marx. Now, there's another way to express the same query plan, but this time more pictorially. So if you think about this subquery, there's a blue one and there's an orange one. So then you can represent that with a tree decomposition of the query. So a tree decomposition is a tree in which every node is a set of variables. So ABC, BCDE, DEF. And then the query plan is just to, you gather some of the input relations or input factors or input functions. You multiply them and marginalize away one of the variables like F, right? And the result of that is a message that is passed to the next node in the tree decomposition or the parent node. And then you compute the next subproblem and then, send the next message up the root. And eventually the output is computed from marginalizing away all the way A, B, and C. And under the right algebra, this is actually called the Yanaka-Kiss algorithm or belief propagation algorithm from Girosporo in 1992. So they are basically the same thing. Now, both of these papers talked about acyclic queries, though. So it wasn't on fractional hypertree width, but it's basically the same idea. Okay, now for the same query, you could have a different query plan. So here, back to Pablo's question earlier, we could have chosen to marginalize away A first, for example, a different variable first. So it turns out that for this query, that doesn't really matter. We will end up with Android 1.5 anyways. But the tree decomposition looks different. So it's no longer a path. In this case, it's more like a tree. And the width of this decomposition is still 1.5. Okay, so now let me somewhat formally define the notion of tree decomposition. So given a query like this, there's a lot of atoms or constraint in the query. So one is R on ABD, another one is T on CBD. You could have, G divided by F is equal to H, and so on. So that's a conjunction of constraints, right? And the tree decomposition is a tree in which every node is a subset of variables, and this is called a bag. Don't ask me why. It's not a bag. It's a set. So every node is a set of variables, and for which the following two conditions have to be satisfied. The first one is that if you look at the set of variables corresponding to one of the atoms in the body, like CBD, for example, then there has to be a bag that contains it. So this atom has to be contained in one of the bags. That's the first condition. And the second condition, this atom G, F, and H, then it's contained in another bag right here, right? So that's a containment property. And the second property is that if we single out any variable, like B, for example, and you look at all of the bags for which B is a part of, then that has to form a subtree. So it has to be connected inside. Those are two main properties. Okay, and it can be shown that the variable elimination algorithm is exactly the same as the message passing algorithm when you draw the tree decomposition, you compose the messages to send up the tree. Okay, so now the question was, we look at our generic query plan, and what we do is we decide on the tree decomposition. Okay? Let's say that somebody gave us a tree decomposition, which is the same as the variable ordering. So if somebody gave us the tree decomposition already, then what can we do? Well, we can run variable elimination, right? And you see that the runtime will be linear in the input plus the output of this portion of the query plan. Now, but then the question is, how do we, compute the minimum representation here? Minimizing this is going to make the blue portion of our meta query plan as small as possible. And now we are back to the earlier question of bounding the cardinality of an intermediate relation. So what do we have? Well, we have that for every bag of the tree decomposition. So this chi function will map a node of the tree decomposition to a bag. So I would think of it this way. You have a tree decomposition like this. And T is one of these bags, right? And this set is chi T. It's the set of variables on the bag. And our rule is basically we need to compute the satisfying assignments for the variables in this bag of the tree decomposition. So just so that you have the right mental picture, that would be let's see, one of these guys, right? All of the triples D, E, F in this blue bag. Okay, this is the chi T, and the bound of that will be n to the 1.5. So think of the blue bag as this chi T here, which we have to minimize the size of. Yeah. Okay, so now we have the tree decomposition, and we have to compute this query one for every bag. One query for every bag of the tree decomposition. And so now let's just plug in our polymetroid bound. Yeah? So we have this query, and the quantity we are interested in is the following. So first of all, we have to minimize over all possible tree decomposition. If you want to minimize this representation, then we better go over all possible tree decompositions, right? And then we have to for each of such tree decomposition, the worst case will be the worst bag of the biggest bag. Right? So that's why this is a maximization. You want to maximize over all bags of the tree decomposition, over all databases, satisfying the same degree constraint of the size of that output. So that's what this expression means. Yeah? So to minimize the middle portion, we have to minimize over tree decomposition, and then the rest is just the worst case bound. So then we know this, right? We have talked about the polymetroid bound. So this will become the min over tree decomposition, and then max over bags tree decomposition, and then max over this polymetroid bound of this h of chi t function. This is the bound we've been discussing since the morning. Right. So that's our query plan. It's very, very simple. To achieve this, right, we just plug in that quantity. So this blue thing now can be made more concrete by minimizing over this middle quantity. And if you plug this in, so there are some corollaries. For example, you can get the fractional hypertree width bound of from the Grohe and Marx paper in 06. Right? And depending on the query, this width could be a lot smaller than the worst case size bound. For example, the width of a tree reaches 1. So the whole thing is just linear time. And thus, the classic Jode-Pearls result saying that you can do inference in graphical model for acyclic models in linear time. Okay, so that's query plan number 1. There are other variations. For example, if we don't use the worst case optimal join algorithm, we could use other join operators. Then you will get some other bounds, like the general hypertree width bound. You can get a tree width plus 1 bound. This is a very common exponent in graphical model inference because their factors are all dense factor, so you don't get any advantage from doing the polymatroid bound because it's very, very dense, just like dense matrix multiplication. And then later on, I'll discuss the submodular width, which is 1 notch below this. That's one variation. The other variation is that so far I have only discussed the queries which has no free variables. You put the free variables in, then it'll put a restriction on the kinds of tree decomposition you can use to minimize over. Because you have to eliminate the bound variables before the free variable, and so that limits the tree decomposition. But the same framework will apply, and then you get something called the FAQ width. Okay, so that's the kind of the easier part of the meta query plan. And finally, let's look at another idea that will kind of put everything together. So here, this is a beautiful idea from Daniel Marx. So it goes like this. So far, we have talked about the representation where we have only one tree decomposition as an intermediate representation. But Marx says, why not choose many tree decompositions? There's no reason for us to choose just one. Okay? So this is now a disjunction over like as many as you want, all of them, for example. Does that reduce the size of the intermediate representation somehow? So this is what I would call tensor decomposition, because it's basically you take a tensor, which is just a product, a factorized tensor, and then you write it in a sum product form, right? And in the sum product form, this is a product of over backs of a tree decomposition, and we know that for every given tree decomposition, you can run variable elimination, and you get the answer out quickly. So all we have to do is to run this variable elimination many times. But we know of how to solve this query from here to here. But now the question is, can we actually do something interesting with this representation now? So I'll give an example that we actually learned from Uri's paper. So let's say you want to detect 4 cycles in a graph, right? Just detect whether a graph has a 4 cycle. So one thing to do is to run variable elimination like before. So then you will stick with either this tree decomposition or that tree decomposition. Right? You cannot do both. But if you do that, then you will get quadratic time, because no matter which variable you eliminate, you have kind of a cross product like join, right? And the join, if A3 is a very heavy degree vertex, right? Then you will join all of its neighbors with all of its neighbors. So then you get quadratic size. So but now the idea is, can we actually mix this up? So let's use both of the tree decompositions. Yeah. So then what does that mean? It means that from the body of the query, we are now going to find tuples to put into either the red tree decomposition or the blue one. So this is an OR, right? So it's a disjunctive representation. Okay. Now, but the question is, how do we even compute this thing, right? Because it's not completely obvious how you would, iterate over the body of this query and then somehow put some tuples in this tree decomposition, put some tuples in the other tree decomposition, that might take quadratic time or even more already. So how do we solve this problem? So here's one trick. It turns out that in a Boolean case, what you can do is this is exactly equivalent to this. So you can kind of pair up the red and the blue. And now you get, you can write this in, I guess this is CNF form, right? So you go from DNF to CNF form. And the beauty about the CNF form is that this is a conjunction, right? So then you can solve each of the sub-problems individually. You solve this problem for this portion, solve this problem for this second portion, and so on. So that means that we now have 4 rules to solve. Instead of one single rule as before, we have 4 rules. And this rule is something called the disjunctive data log rule. It has a very, very interesting semantic. So I'll explain it in a bit. Okay? So before, when we were talking about conjunctive query, there's only one atom or one relation in the head, right? Then you would existentially quantify away some variable, and then you put output tuples in there. But this is a disjunction, so its semantic is very interesting. So let's look at this semantic. So the answer to this query, this is called a disjunctive data log query. The answer to this query contains 2 tables, a red table and the blue table. The red table is on 3 variables, A1, A2, A3. The blue table is on 3 variables, A1, A2, A4. So that the following is satisfied. That if you have a tuple that satisfies the body, so if A1, A2 is in R12, A2, A3 is in R23, and so on, A4, A1 is in R41. If you have a tuple that satisfies the body, then the tuple only has to satisfy either the red constraint or the blue constraint, but doesn't have to satisfy both. So you have kind of some flexibility in constructing the solution, because the solution only has to cover a part of the query in some sense. So the way I would typically visualize this is like this. So this is in 4 dimensions, but I'm drawing this only in 3 dimensions. So suppose that you have a point like this. Then you have this table and this table. So there are two tables in the head, and the point is in 3 dimensions. And this table is in 2 dimensions. So this is maybe A, this is B, this is C. Then in order to record that I have seen this point, you can either put it here or put it here, but you don't have to do both. So that's the semantic of the disjunctive data log rule, right? So I have like a bunch of points in 3D, right? It's like this body here. But then I will kind of somehow record the existence of those points by doing this, for this point, I will store this, let's say. For this point, I want to store that shadow, and so on. And that is in some way a compression of the 3D points. Yeah. Go ahead, Remy.
So with this contract T123 and T124, so this doesn't uniquely define.
No, it does not uniquely define the solution. And there are actually a couple of 3 different semantics for this. And you can think about kind of a minimal model semantic, where you require the solution to be minimal, like under set containment, for example. That could be one semantic. I'm just giving you the definition of what it means to be a model, but I didn't give you what it means to be the model. So just a model. That's enough for our purpose. Okay, so now here's the most interesting part. Given a rule like this, then what is the output size? Right, so the output size of this rule is going to be, well, we have 2 tables, right? We have table 1 to 3 and table 1 to 4. And the output size, I'm going to define it to be the maximum over those 2 tables. You can take the sum too, it doesn't actually change anything, but the maximum is more elegant. It's basically the worst case shadow, right? If you have a bunch of points in 3D, and you take a portion of the shadow on one side, a portion of the shadow on the other side, and take the maximum of the shadow. So you basically have to balance the shadows. You cannot cover everything with just one shadow.
Can I think of it as replacing the design with T1, 2, 3, 4, and then projecting it out to 0, 1?
I guess one way to compute a model would be to realize all of these points and then decide which shadow to put it on.
Right, and to maximize it and just do the projection.
That's right. Yeah, you could do it that way, but that would kind of defeat the purpose because listing all these points will be quadratic. Yeah. So the idea is to somehow compute the shadows without actually computing all of the points in 3D. Okay, so now, so here's our plan. So think of this B as the red, blue, 1, 2, 3, 1, 3, 4. Backs in the head of the rows, right? So now we have rewritten the conjunction over 3D composition over into the CNF form, right? Where we now can solve each of these rules separately. So this is a disjunctive data log rule, so that's this guy. That's exactly this guy right here, right? Except that we are arranging this over a humongous collection of rules. But this is one of those rules, right? And then we already have a definition for the size of a model for this rule, which is this definition right here, the size of a model is maximum over T1, 2, 3, T1, 3, 4. And here we're just taking this maximum over all possible colors that occur in the head, right? And now the problem is how do we bound this output size? How do we even bound it? And then what's the algorithm to compute this, right? So we are back again to the same setting of bounding the output size of a rule, except that the rule is no longer a full conjunctive query. It is a disjunctive data log rule. It's the same story as before. And it turns out that you can do something similar, right? You can bound the size of a disjunctive data log rule using the polymetroid bound, just using the entropy argument and the polymetroid bound. The only difference is that there's this extra min that goes into the picture. And if you would like an exercise for your students, this is an excellent exercise. Just show them the entropic argument for full conjunctive query, and then you can ask them to prove this bound. It's very similar, but it's subtly different. It takes about 3 lines of argument, so it's a good exercise to do. But now that we have the polymetroid bound for this, and we can play the same game and go back and do the Shannon flow inequality and come up with the use the Panda algorithm to solve the query. So let me just go to the 4-cycle example and see how this bound works in practice. Yeah. So remember that one of the disjunctive data log rules that we had from the 4-cycle example was this one, right? 1, 2, 3, 1, 2, 3, 4. So the bound says that the maximum size of the model in the worst case. Remember, this is a little tricky because this is a maximum over a minimum. You see, it has a little bit of trickiness because you have to compute kind of the minimum model and then you take the maximum over the worst case. So it has a bunch of max and min going together. Right? But in any case, the bound says that this is smaller than the max over the min of these two entropy values. So HA123 and HA234. Okay? This is what the polymetroid bound says. And once you have the polymetroid bound, you can play the same game. So the min of 2 quantity is less than the average of the 2 quantities. Now, the average, you can now apply, submodularity and monotonicity and all of that to show that this is just like the Shearer's inequality, actually. However, on the left-hand side, there are not two things, not just one as before. It's just like Shearer's inequality. Now you have this bound, and now because this is less than log n, each one of them is less than log n, so you get 3/2 times log n. And this is essentially why in the AYZ algorithm for 4 cycle, we get the runtime of n to the 1.5. It came from this. Okay, so that's our realization of idea 2, right? So all we did was that we replaced this mysterious blue quantity with a collection of 3 decompositions. And then we have the worst case, bound using the polymatroid bound. And well, we need a worst case optimal join algorithm for a disjunctive data log. So this is a little bit more general than before. But we already had the Panda, the algorithm is in the pudding framework, so we can apply the same idea. And that's what we end up with the end. So the very last thing to mention is that where does the Shannon flow inequality come from? Because before it was just a max over h of v, but now we have a max over a min. So that seems to be a little bit hard to deal with, right? Now it turns out that you can show that from the constraints, you can turn this min into a linear combination. So it's much easier to maximize over a linear combination of things than just maximize over the minimum. And now you have kind of a linear objective and linear constraints. So then apply Farkas's lemma, you get the Shannon flow inequality. So that's just one extra technical step that we have to prove, turning this maximin into max of a linear combination. Okay, and that's how we get the Shannon flow inequality. The only difference from before is that now this is a linear combination over h's on this side. Okay, so I'm not going through the proof sequence anymore. It's the same thing as we did before. So one of the corollaries is that we get, like for example, the submodular width result from Daniel Marx using this framework. For example, we could get the AYZ result where you can detect case cycle in, in quadratic, n to the 2 minus epsilon time. Yeah, so the submodular width is a very, very powerful framework. And if you have general constraint, then you turn it into this format. So it will be a little bit finer than just d to some power. So I guess back to someone's question earlier, I guess this is kind of, parameterized complexity, fine-grained complexity type of result. Because this is a function of both the constraints and the query. Go ahead, Dan.
Just a question. Does this complexity also hold for counting case cycles? It's only for detecting whether the result is 1.
Yeah, a great question. So it doesn't quite hold for counting simply because in our query plan, and then we go all the way back here in a generic query plan. Now, for counting, we'll have to replace this with a sum and this with a product, right? And in order for the sum and product to be correct, they have to be disjoint. Like you cannot overcount. If it was a sum over a product and if this product occurs in 2 different sums, then we are overcounting the output. So then the 3 decompositions will have to be somehow so that you have this disjointness property. And we have a paper together on this topic. So you could do something like that, but it's not as clean as this thought. And so that's one. And then the other issue is that this rule does not apply if you put in here a sum and this is a product. Right? So a sum of these two is not going to be a product of the sum like this, simply due to overcounting. But you could apply this, I think, maybe with idempotent semi-ring. So if this was, if the summation is idempotent, then something like this might be okay because double counting doesn't play a role when A plus A is equal to A. So that's fine. So like a min.
In any distributed lattice.
Any distributed lattice. So that would be fine. Okay, so I think that's basically the kind of very high level query plan for this, and I think I'm done. So I'm not going to the examples anymore because you can kind of use the same idea of proof sequence to join operators to achieve the same result. Let me just say a few things about the open problems. So in order to put this into practice, the range of 3D compositions we have to range over has to be very small, because when you apply the DNF to CNF rewrite, when you distribute the sum over the product, it explodes, right? It's the number of rules that you have to answer explodes. So the question is, can we restrict the number of 3D compositions? Maybe some of them are completely irrelevant for obtaining the bound. So reducing that would be great. The abstraction that we built is some product queries. Obviously, they do not capture all possible practical queries, right? So they are just one class of queries. They are pretty okay for some, aggregation, simple aggregation type of queries. But in practice, we have many more. We could have, queries with top K, rank enumeration. I guess, Mirek and Wolfgang and Nikos will tell you more about those classes of queries. You could have queries with arithmetic circuits, so you could sum and product and exponentiation, and all of that are very common in machine learning. Those are much more difficult queries to deal with. We need a general theory for tensor decomposition, not just the submodular width, but for queries with, let's say, inequality or disequality or other built-in functions. I have some examples of tensor decomposition working for these, but they're not general enough. Yeah, so that's it for, we are at time. And thanks for suffering too. Yeah.
Yes, okay. Could you please go to slide 27?
This one?
Yeah. So I'm trying to understand the theorem. What model do you have in mind? You told us there are models and models. And is it any model or some the stable model semantics? What do you have in mind here?
I just have a model. So, yeah.
But what is the model here? Because there are at least three different semantics for design. There is stable models. Which is the one that you really want?
It's exactly.
Some of the disjunctive data log computations aren't hard. You can very easily encode free colorability.
Yeah, so in our case, we only need one model, and then the semi-joint reduction of the variable elimination part is going to eliminate all of the redundant tuples. So we only have to compute just one model. As long as it's within this bound, then the query plan goes through.
I see. So computing a better model doesn't buy you anything.
Doesn't help us in the sense of worst case optimality.
That's interesting. Okay, thank you.
I should also mention these are not recursive. These are non-recursive queries. So yeah, so I don't think stable model.
I see. So that's right. I missed that. So these are just continuous or conjunctive queries.
Well, just a conjunctive query to put the union on the left. And the game in town is to reduce the size of both tables on the left. That you
but if you do this for data log programs with disjunction, it will change completely. Like the model where play a role, which model?
yeah, especially if you have recursion, then absolutely here. All things.
Okay, I understand now. Thank you.
So I have my big questions. So getting back to, so here's what I understand. To enumerate all triangles, we need time n to the power 3 by 2. what is the best time known for checking the triangle? What is the best time known for counting the number of triangles?
He uses matrix multiplication.
Oh, but we have the listing presentation of the triangles, not the matrix representation, but it's the listing.
So in terms of your n, it would be n to the, if
Matrix multiplication can be done in a square time, it will be n to the square.
I see. So there is something that depends on omega. Is there a difference between checking and counting?
all the algorithms that check count as well.
Okay, so checking and counting the same. What about the fourth cycle?
For direct first cycle, yeah, so it's a little bit slower. So you would have n to the 1.5 here, it would be n to the 1.48 with the current
So it gets difficult because it means that these submodular weights that we have for upper bounds, they are not the best lower bounds.
Yeah, I mean, for detection, there's faster algorithms.
Right. And the submodular weight only works for detection. That's
Yeah.
so pick open problems. What is the right bound? What's the right instruction? More questions?
Yes, yeah. What happens if you have projection? I assume this is for queries.
Oh, you mean projection in addition to data output?
Yeah.
So I think these do have projection. So in a data output, there's an implicit existential quantification of variables that are not in the head.
No, I mean the query itself, if it has projection. Does the same framework still?
Oh, yes, yes. Thank you. So,
Not a Boolean query, but a query with some output variables.
yeah, so it's the same that we range over the 3D compositions, a certain set of 3D compositions capturing this the free variables. And then once you have those 3D compositions, you can do the DNF rewrite or CSV rewrite.
So we need to add the output variables to the node to the 3D compositions.
You could do that, or you can range over the free variables. I mean, the 3D composition for which the free variables form a sub 3D composition up top of it. The free connects.
More questions? Okay, let's time count and let's cover this point.